Record. Hey everyone, so today is just going to be a review lesson on everything that we've done so far. So first up, we're going to be talking about the types of models, which we did in our very first lesson. And one of the key parts of this is understanding the mathematical terms that we associate with a lot of the physical properties. So that's position, distance, displacement, speed, velocity, and acceleration. Out of these, position, displacement, velocity, and acceleration are vectors because they include a direction, which in other terms can be thought of having a negative and a positive aspect to it. Distance and speed are scalars, so they will always be a positive number. And the graphs that we also talked about are position versus time, velocity times time, and acceleration times time. And the example that we discussed, which is really helpful because you can see the difference between all three of these graphs, is when a car is traveling at a constant acceleration. So as we see in this bottom graph, which is the acceleration times time, the value is absolutely constant. However, because velocity has the slope of acceleration, so the slope of this line will be this value. You can see that has a constant slope. And same thing with position versus time, it creates this curved graph. And now for problems to go along with this. The very first problem that we're going to do is a graph to discuss how to represent this motion. So we'll give you around 5 seconds to pause, work it out, and then we'll discuss the solution. So first up, position versus time. And as you can tell by this, when a ball is tossed up directly in the air, you can visualize this as a ball going up, slowing down, and then stopping again. And that's why it creates that arch shape for the position versus time. And when we look at the velocity times time, which is what's associated with this graph, you can see that it has a 0 point at the same place, which is 1.5 seconds, at the place at which the ball reaches its maximum point. And this is also the place that if you were to draw a tangent line, the slope would be 0. And if we also connect these two, you see that it begins with the position versus time begins with a sharp and high slope, reaches 0, then becomes negative, and then increases in the negative direction again. And this is the same pattern that you see in the velocity times time graph. We start off with a really high positive value, reach 0, and then go towards negative again. And a key point in understanding this is that a ball tossed up straight in the air would have a slope of negative 9.8 meters per second squared. So therefore, the slope of this graph would be negative 9.8. And what you see in the acceleration times graph as well is that it's a straight line that goes just above 10, which is approximately 9.8, and represents acceleration versus time.
The next unit we talked about was kinematics, which is a way of analyzing motion with constant acceleration, where we have three main formulas. The final velocity is equal to the initial velocity plus acceleration times time. The final position is equal to the initial position plus the initial velocity times time plus half of the acceleration times time squared. And the square of the final velocity is equal to the square of the initial velocity plus 2 times the acceleration times the displacement. The way we solve a kinematics problem is we analyze the scenario. So it's just like looking at what the problem is asking for, draw a diagram to help you visualize what's going on in the problem, and then you want to identify the variables, so like finding out which ones you have and which ones you need to find, which leads to choosing an equation, and then you just plug in the values you're given, and then you get your answer. So for our practice problem here, a juggler tosses a flaming torch directly upwards at 3 meters per second. Determine the following. How much time does it take for the torch to come back to his hand? The greatest height the torch reaches, and the height of the torch when its speed is 2 meters per second. And we'll give you a few seconds to pause the video and figure it out for yourself. Okay, so to find how much time it takes for the torch to come back to your hand, you use the formula T equals 2 times V initial divided by G, which you can derive from the other formulas, getting around 0.61 seconds. The greatest height, you can also derive this from the other formulas, specifically the third formula, and setting the final velocity equal to 0 and acceleration equal to g, and you get around 0.46 meters. And the height of the torch when its speed is 2 meters per second, using the third formula again, is 0.26 meters. Our second example problem is similar, except we're given different variables. Randolph's friend challenges him to throw a tennis ball in the air for 6 seconds. What's the minimum speed that Randolph needs to throw the ball at? How high does the ball go? And what speed does Randolph catch the ball at? And we'll give you another 5 seconds to figure this one out, or to pause and figure it out. Okay, so the minimum speed you take, or you have to use the same formula as the first one, but now you're solving for V, and you get around 29.4 meters per second. And the height of the ball, you're going to use the same formula as last time for the same, the last problem. And you get 44.1 meters. And for C, you get negative 29.4 meters per second. And the reason why that is because when you throw a ball, all of the speed is going to come back because a parabola is symmetrical. And all of that speed is going to come back, but this time it's negative since it's going downwards.
And the next topic that we're going to be talking about is projectile motion. And it's really similar to solve these type of problems as it was with the kinematics that Mark was talking about. The main idea to understand with this is the difference between the vertical component and the horizontal component. When we look at the vertical component, it's important to recognize that the acceleration will be a constant, negative 9.8 meters per second squared, which would be the acceleration due to gravity on Earth. And again, remember, this is the number used when we're on Earth. And another thing that's important when we're solving is to recognize that the vertical velocity will be 0 meters per second when it's at its peak. And it's easy to visualize this. If you're throwing a ball, as you throw the ball, when it reaches its really max velocity, you can see it slowing down and then speeding up again as it returns back to the ground. With horizontal component, what's interesting is that the final velocity is the exact same as the initial velocity. And as you can tell by these two characteristics, the components of velocity are completely independent of each other. And therefore, you have to solve as though they're completely independent with different equations. And to solve and to recognize which one is which, we use the formula that the h component, the horizontal component, is the velocity times the cosine of theta, and the vertical component is velocity times sine of theta. And this image is really helpful when we try to think about this, because as you see, if this cannon shoots out, we have that the horizontal velocity, which is Vx, is exactly the same throughout the entire motion. But the vertical component, which starts with a 0, goes to negative 9.8 to negative 19.6. So you can see that the rate of change, which is the acceleration, is negative 9.8. And it's increasing as it goes down to the ground. And each of these components are completely independent of each other. So here's the first problem that we're going to solve. So a stone is projected vertically upwards with a velocity of 12 meters per second. Calculate or find how long it took for the stone to reach its maximum height and the maximum height it reaches. So again, around 5 seconds to pause and try out the problem. So first up, how long it took. And really the main point that we want to emphasize with this problem is that you have to solve this by realizing that when the stone reaches its maximum height, the velocity will be 0. So therefore, you can use the following equation and set v final to 0. And you know the initial velocity is 12 because it's given, and that the acceleration for the vertical component, which is what we're solving through, is 9.8. And we get 1.22 seconds. We have to use the vertical component here because if you think about it, with the horizontal, there's no real way to distinguish which point in time we are because the velocity is constant the entire time. The actual point at which the ball reaches its maximum and reaches the ground is determined by the vertical component. And for the maximum height, if we use this equation, we basically just need to plug in the values we already have, which is by how we solved the time. Plug that in and we get around 7.34 meters. And a lot of times in AP problems, instead of being two different problems, they'll have it as one together and just say calculate the maximum height. And this step is basically just a standard that you can use every time. First, find out the time by using velocity final as 0 meters per second, and then you can find the height. Our next problem. A tennis player strikes a ball with his racket just as the ball reaches the ground. The ball leaves the racket with a speed of 6 meters per second at 50 degrees to the ground. So we have around 4 problems here. Calculate the initial vertical component of the velocity, calculate the initial horizontal component of the velocity, and then calculate the time taken for the ball to travel 2 meters to the net after leaving the racket, and then show by calculation if the ball will go over the net if the net is 9.9 meters high. So again, around 5 seconds to pause and solve. So first, these 2 problems is basically just using the formula from below, from the earlier slide. That's that the vertical component is the initial velocity times the sine of the angle at which it is projected at, which is 50 degrees in this scenario. The horizontal component is the cosine. And a lot of times you can just leave it in the trig form because the actual answer will be some sort of decimal. And then calculate the time. So for this, it's again just using one of the kinematic formulas. And we can use the time that we have. Because it's almost at the ground, we can assume that the initial x is just 0. But we know that we need to find out what the time is when it's at 2 meters. Therefore, the final x is 2. The velocity, as we saw, is the horizontal because we're dealing with the horizontal movement. So therefore, we have to just specifically use the horizontal component of velocity. And therefore, we also know that in the horizontal component alone, there is no acceleration. So that part is just 0. So we know that 2 must equal 6 times cosine of 50 degrees times t. And we saw that you get time is around 0.5 seconds. And for this problem, we actually use the same equation. But instead of dealing with just the horizontal component, we now have to think about the vertical component because we're looking at how high the ball can go. And therefore, the velocity is now 6 times sine of 50 degrees, and the acceleration is now negative 9.8. Here it says negative 4.9 because it's just divided by 2 already. And we get that x is 1.06, and therefore it will go over the 0.9 high.
Next, we talked a bit about forces. A force is a push or pull that can affect the motion of an object. A force is exerted on a body, or forces exerted on a body are often represented on a free body diagram. Arrows show direction and magnitude of a force, and a net force of 0 means there's no acceleration, or in other words, it's in equilibrium. There are a few forces we talked about. We talked about surface. We talked about, the first types of forces, or what? I'm sorry, where's normal force? It just says surface pushing on.
Yeah, I think it got deleted accidentally. Sorry, guys. The first one's supposed to say normal force, and the description is
Okay,
surface.
so
Yeah.
normal force is what you get when a surface is pushing perpendicularly on an object. So in our diagram, it's normal forces pointing upwards, but sometimes you can have normal force pointing in different directions. So if you've got like a slope with a box, normal force is going to point this way. It's going to point perpendicular to the slope. We also learned about friction, namely static friction, which is what keeps an object from moving, represented by F sub s is less than or equal to mu sub s times n. The reason why we have a less than or equal to sign is because we're simply saying that static friction continues to increase and increase until it can't anymore. And when it can't increase anymore, it starts moving. The object starts moving. And the friction you get when an object is moving is kinetic friction given by F sub k equals mu sub k times n, where n is normal force. And this is what slows down moving objects. We also learned about tension force, which is what you get when a rope or a chain or some other sort of object like that pulls on an object. And an applied force is generally some force caused by a human. So something like a human pushing on a block, or someone carrying something. Our first problem is just a free body diagram of a car coasting to the right and slowing down. And we'll give you 5 seconds to pause and figure it out. Okay, so when we draw a free body diagram, we know that it's slowing down. So we know the acceleration is going to be pointing in the opposite direction as the motion. And since we're told that it's going rightwards, our acceleration should point leftwards. And then, of course, you have to add the force of gravity, which is its weight, which is pointing downwards, and the normal force, which is, in this case, opposite the the force of gravity with the same magnitude.
And just before we move on, something I want to point out is that a common misconception is that because the car is moving towards the right, that the net force should be towards the right. But that's not the case. In this case, we're told that the car is coasting and therefore there's no applied force. The engine of the car is not applying anything for the car to be moving forward. Instead, it's likely that a brake is being pushed down, causing an acceleration in the reverse direction, like Mark said, causing the applied force. And therefore, there is no force pointing forward, even though we are moving towards the right.
Yeah. A college student rests a backpack on his shoulder. The pack is suspended motionless by one strap from the shoulder. Draw a free body diagram for the situation. We'll give you another 5 seconds. Okay. This problem, you have tension pulling upwards. And to the right, I guess, because is that just a badly drawn arrow?
Basically, the idea with this one is it is a bit complex, but because I would assume that it's resting on your back, so the back will provide some sort of normal force. So like if you imagine when you hold your back, it's at your backpack, it's at like slightly of an angle, the strap.
Okay, yeah.
That's what the tension's accounting for.
Okay, and then you've got gravity pointing downwards. The thing to make sure here is that, or to take note of, you don't have to draw this perfectly, but this angle here is important because it determines the, I don't need that. It determines how much magnitude the tension force is, because whatever it is, this horizontal or vertical component here, it has to be equal to Fg. Or it has to have the same magnitude as Fg. That way it's it's not moving up or down.
And in the same way, the normal force, which you can visualize as like your back touching the backpack and pushing it off, has to be equal to this horizontal component.
Yeah, the horizontal component, that has to be Fn with a negative sign. Mm-hmm. So that when you add them, you get 0.
Okay, and now Newton's laws. And there are 3 laws of motion by Newton. The first one is that an object at rest will remain at rest, and an object in motion will remain in motion at a constant velocity unless acted upon by an unbalanced external force. And this is basically the concept of inertia, that an object prefers to stay in its current type of motion rather than change. And Newton's second law is basically F net force equals ma, which we often just call F equals ma. And Newton's third law is that for every action, there is an equal and opposite reaction. And these words are said a lot, and basically what it means is that if you apply some sort of force on a book or a desk, the object is pushing at the exact same force, but in the opposite direction. So our first problem, which is related to Newton's first law. A 2 kg object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep the object moving at this speed and in this direction? So just think about that for a couple seconds, and then you can pause, think about it, and we'll get back. And basically, when you think about this, the main idea to take away is that the object has to continue moving in the same speed and the same direction. And therefore, there is no force. So net force is 0 newtons. And it is, again, a little weird to think about because the object is moving, but there's no acceleration. So with F equals ma, which actually connects to the second law, is if the acceleration is 0, then the force has to be 0 newtons. And now our second problem, which is related to the second law. A 7.26 kg bowling ball is at rest and at the end of the bowling lane. With this information, answer the following questions. What is the net force acting upon the ball? If you push the ball with a force of 22.8 newtons, which induces a negative 2.3 Newton frictional force, what is the net force while you push the ball? What is the acceleration caused by this push? And following your push, the ball rolls down the lane at 4.2 meters per second at a constant velocity. What is the net force on the ball as it rolls down the lane? So again, 5 seconds, pause the video and give it a go. Again, for A, it's exactly what we were talking about before. The ball is not moving and it's just sitting on the table or on the floor with 0 newtons. And there is, of course, going to be the gravitational force pulling it down, but at the same time, there's the normal force pushing it back up. And both of those will cross out, and the net will be 0. If we push the ball at 22.8 newtons, and we also have a frictional force in the opposite direction of 2.8, the net force is simply, you just need to add them up. And that gets you 20.5 newtons. And the immediate use of this information is to figure out what the acceleration is. And this is exactly what the second law tells you. The net force is equal to the mass times acceleration. So 20.5 must equal 7.26 times the acceleration that we're trying to find. And therefore, we can say that the acceleration is around 2.82 meters per second squared. And last, again, just reiterating that idea that even though you're traveling at a constant velocity and you are moving, the net force of the ball is still 0 newtons. And finally, the third law of motion. Manuel is holding a 5 kilogram box. First, draw a free body diagram for Manuel's hand and the box. Then, how much force is the box exerting on him? How much force is he exerting on it? And if Manuel weighs 375 newtons and is holding the box, how much force is the floor exerting on him? And include direction. So 5 seconds, pause, and give this a shot. So first up, the free body diagram. So for the hand, we have one, the applied force pushing it up. And this is sort of hard to put your head around. And the idea behind this is that your muscles in your hand will be putting some sort of upward force to ensure that your hand can stay where it is, right? You're holding the box up, and that's your muscle using energy and keeping your hand from just falling downwards. And gravity, of course, every object has gravity pulling downwards. And the normal force will be the box, which is on Manuel's hand, pushing downwards. And for the box, we just have force of gravity and the normal force, because the normal force is from the hand pushing it up and gravitational force as normal. And what's important in this is that the normal force and gravitational force for the box must be equal because there's no acceleration. And at the same time, the force of gravity plus the normal force should be equal to the applied force for Manuel. And that's, again, so that we ensure that acceleration is 0. So how much force is the box exerting on him? And that's just the gravitational force. If we look at this, the only force that's interacting between the box and Manuel, or on Manuel, is caused by the box, is the gravitational force being pushed downwards. That's 5 times 9.8, which is approximately 49. And as per Newton's third law, the whole idea behind this is that if the box is exerting 49 newtons, then he should also be exerting 49 newtons. However, it's in the opposite direction, so it's upwards. And if Manuel weighs 375 newtons and is holding the box, we can just tell that the net force that Manuel and the box are exerting onto the ground is 424. And therefore, the ground must be exerting the exact same force in the opposite direction, which is upward, which we can think as normal force. And this is also not his hand, this is his entire body.
Our next section is uniform circular motion. This is where we have a ball that's moving, or an object that's moving in a circle at a constant speed. Here we have a constant speed, but also constant acceleration. The reason why that is because we're always changing direction. We don't have to have an acceleration simply because speed is changing. We see that acceleration is perpendicular to the motion, impacting the direction of the velocity rather than the magnitude. And we have the centripetal force is given by m times v squared over r, or in other words, centripetal acceleration is given by v squared over r. Our example problem is a 925 kilogram car rounds an unbanked curve at a speed of 25 meters per second. The radius of the curve is 72 meters. What is the minimum coefficient of friction between the car and the road required so that the car does not skid? We'll give you 5 seconds to pause and figure it out. All right. So the first thing we want to do is we want to say that the centripetal force is going to be equal to the friction force, because otherwise you'll have the car going or something. So we have the friction force is equal to the kinetic or coefficient of kinetic friction times a normal force, or mu k times mg in this case, and centripetal force is mv squared over r. And then we just set them equal to each other. We can divide out m, because we know it's not going to be 0 because we're given m. M in fact doesn't matter. And then we say, well, mu k is just v squared over r times g, and doing some calculations, we get 0.89 as the coefficient of kinetic friction, or the minimum coefficient, that is.
And also just one thing before we move on, like a lot of people don't recognize that coefficient of friction does not have any units. It's just a number that represents how much of resistance an object can have from a motion of another object. So just remember that when you're solving these problems.
And the way you can think about that is simply, if you look at the kinetic friction formula, friction is a force, and we already have a normal it's something times normal force. And if our something being the coefficient of friction had units, that would mess up our units in the end for friction force. Our next problem is a 2.7 times 10 to the 3 kilogram satellite orbits Earth at a distance of 1.8 times 10 to the 7 meters from Earth's center, that is, at a speed of 4.7 times 10 to the 3 meters per second. What force does the Earth exert on the satellite? And we'll give you another few seconds to pause and figure it out. Okay, and here we just set the centripetal force equal to mv squared over r, and just plug things in, and we get 3.3 times 10 to the 3 newtons. And the reason why it's this simple is because the force exerted on Earth may be gravity, but since it's what's causing the satellite to move in a circle, it's still just centripetal force.
Okay, and now gravity, which is our last section of this review slideshow. So the main ideas in this one is first understanding Newton's law of gravitation, which is basically just the formula. So the gravitational force is the gravitational constant times mass 1 times mass 2 divided by the distance, which is r squared. And therefore, when you want to derive the acceleration due to gravity, we just set one, we can just use this formula. So the acceleration is basically the gravitational force divided by one of the masses. And this is conceptually just Newton's second law, F equals ma. And therefore, if we put in the equation of that we just said before, we get that g, the gravitational constant, times m1 times m2 divided by m2 times radius squared. As we cancel things out, we get that gravitational force times m1 divided by r2 is the acceleration due to gravity. And on Earth, if you plug in Earth's radius for r and m for Earth's mass, you get approximately 9.8, which is the value we've been using basically this entire time for acceleration in the vertical component of projectile motion. Another main idea are Kepler's 3 laws. And you can go back to our other slideshows for more specifics on these, but The main one that we use on the AP exam is the ratio of the period squared divided by r cubed, the radius, the distance cubed. And this is a constant for every planet orbiting the sun. And it's just a really cool and very important idea to recognize when we deal with gravitation.